Hello, we're Team Innovators, Diego, Alan, Mobby, and Marina, and today we are presenting our project. In different industries, in all steps of engineering, from modeling to functioning factory, you need to know certain qualities of fluids going through a system. Sometimes they can be measured directly, sometimes you need to calculate them, and in certain cases you need to be able to predict certain outcomes. One of these cases would be draining a tank. In particular, tank discharging freely into atmosphere through an orifice. And goal of this project was to study such a setup and try to predict the draining time. Here you can see our setup. It's suspended over a sink on a stand with a circular tank discharging through the bottom. In order to be able to predict the time, we need to come up with a formula, as in most fluid dynamics problems. Two equations were used: Bernoulli equation and continuity equation. Through further analysis and derivation, we came up with final formula for time. However, it's important to keep in mind that this formula only works for perfect and ideal conditions, and it does not account for losses. So in order to be able to apply it to real-life problems, we need to find a coefficient. In order to do that, we need to perform an experiment and compare experimental results to our theoretical guess. So Alan will be able to explain to you how exactly we came up with this formula. Alan?
Thank you, Marina. Alan Kefa. As we said earlier, to be able to solve this problem, we make some assumptions. We assume that the fluid that we are using is invisible, it's an invisible fluid, that the water, of course, the water that we are using is incompressible, and that we decide to neglect the air density. We said earlier that to solve the problem, we apply the Bernoulli equation. We also apply the continuity equation, and from these two equations, we were able to come up with a differential equation that we solve using a separation of variables. The result of this differential equation solving is what you can see here, that relation that is related to the height of the water in the tank with the time that is needed to drain that water from the tank. Diego will go ahead with the next section of our presentation.
Thank you, Alan. I'm Diego. I'll be covering the methodology. In our methodology, we had to use these materials: a cylindrical tank that will be holding the water, and we had to use, we were going to use a ruler, but instead we decided to use measuring tape in case the dimensions are longer than 12 inches for a ruler, and we're going to have a standard stopwatch like the one that we use in lab to measure the time that it takes for our experiment to take place. And the adhesive that we're using is waterproof, so because we're going to be dealing with water. And the cork will plug in the orifice that we're going to have in our tank. This is the setup right here. The orifice will be located right here. It'll be a 1/2 inch orifice that we'll probably be making with a push drill or some sort of drill. So the procedure will be, we're going to fill up the tank with water using probably a coffee pot or so until we reach the predetermined height of the tank, at which time we're going to get our stopwatch, and the moment that we release the cork from the bottom of the tank, we're going to start our stopwatch, and we're going to record the amount of time that it takes for the tank to drain. The tank that we're going to have is probably going to be transparent, so it'll be easy for us to determine exactly when the tank is completely drained. And after that's done, we're going to repeat all the steps until the predetermined amount of data points are obtained. And with that, I'll leave you to Moby.
Thank you, Diego. My name is Moby, so I'm going over the expected results from modeling and the significance of those results in real life. So first of all, like Alan said the other time, our modeling is based on Torricelli's equation, Bernoulli's equation, and the continuity equation. So based on that, we're able to arrive at that empirical equation that relates the time and the height and the time needed for draining the tank. So as you can see, that relationship is quadratic in nature, so we expect a quadratic relationship between the time required for draining and the height of the tank. So we're going to compare that to our lab view simulation. And also, our model is an approximation of the border's mouthpiece, which is just a short mouthpiece with a length equal to the radius of the orifice. So in real life, we have data readily available for the coefficient of contraction for a typical borderless mouthpiece. So the result of the experiment is to be, is expected to be in that range too. So if you have any results that deviate a lot from 0.5 for the coefficient of contraction, so that means something is wrong with our setup. So we try as much as possible to compensate for whatever is responsible for that. So having said that, these are the likely reasons for deviations and anomalies. First of all, in most cases, an orifice is considered small if the diameter is less than 2.5 inches and the head is less than 3 feet. So as you can see, our model is very, very small. So that means that we're neglecting lots of real life scenarios that will account for deviations from the typical theoretical value of coefficient of contraction, and also the corrugation in the tank. That's a frictional loss and that's a major head loss. That will account for deviations too. And the difference between the pressure at the top of the tank and that at the bottom, that will affect our results a lot. And finally, the uncertainties associated with the measurement, like the dimensions of the tank and things like that, that will affect our results too. So, and that brings us to the application of our design. It's applied in oil and gas industry. Many times it's required to drain the tank, the overhead tank, probably at the end of the year for servicing. And the beverage industry, as you can see, the orifice is open directly into the bottles. If the timing is not done right, it's either the bottle is overfilled or underfilled. So that's a practical application. And also the novelty glass, that's been in existence for a while. Everybody knows about that. And the hot tub, if you're trying to clean your hot tub, you might want to know how long it takes rather than just sitting down there. And also when you're servicing your tub, your pool too, in the summer. And that brings us to the end of the presentation. Hope you guys enjoyed it. Thank you.